melts. 3 ice cubes at a temperature of 0 degrees Celsius are dropped into a container of water at a temperature of 24 degrees Celsius. Okay, so have the ice cubes and water with the different temperatures. Next, the mass of each ice cube is 25 grams. Because we have 3 ice cubes, so the total mass of the ice cube it is 25 times 3, so 75 grams. Okay, next, the mass of the water is 200 grams. Okay, this is the mass of the water. Okay, the ice melts so that the temperature of the water decreases. Okay, this is the key point of the question. So the heat needed the ice is to melt, and the heat released by the water is to decrease the temperature. So we use a difference equation of the heat between ice and water. Okay, next, the thermal capacity of the container is negligible. It means that the container didn't absorb or release the heat, so we only focus in ice and water. And we need to assume that no thermal energy is exchanged between the water and the surrounding. Okay, so we need just focus in ice and water. Okay, the ice and water with a different temperature. This is 0 degrees Celsius and the water is 24 degrees Celsius, and the mass of the ice is 75 grams. And the mass of the water is 200 grams. Okay, based on these questions, we also know the following informations about the specific latent heat of fusion of ice is 80 calories per grams, and also the specific heat capacity of water is 1 calorie per gram degree Celsius. Because the specific latent and specific heat capacity is known in a gram, so we don't need to convert the mass of ice and water in kilogram. We just use the grams to make it easier, right? Okay. So first, we need to calculate the heat needed by the ice to melt. Okay. First, because in this question, we know the statement the ice will be melt and the temperature of the water will be decreased. So the heat needed for ice is to melt, to change its pace from ice to water. So we use the equation for latent heat. So Q equal M times L. M for mass and L for specific latent heat. Okay, the mass is 75 and the specific latent heat of fusion of ice is 80. So it is 6,000 calories. Okay, this is the heat needed by the ice, and we assume that all ice will be melted. So this is the heat needed to melt all of the ice. Okay, 6,000 calories. And then next, B, we need to calculate the heat released by the water. So based on the question, the temperature of water decreased. So the heat that released by the water used to decreasing the temperature of the water. So we use the equation M times C times delta T. Okay, M for mass, C for specific heat capacity of water, and delta T is the temperature difference. Okay, so mass of the water is 200 and then the C 1, and the temperature difference is 24 with 0. So it is 24 negative 0. Okay, so it will be 200 times 24. So the result is 4,600 calories. Okay, so this is the heat for water. Okay, we already know the heat needed to melt the ice and the heat released by the water. Okay, and then to answer number C, does all the ice melt? And we need also to explain it. Okay, so we look at the heat needed by the ice and the heat released by the water. To answer number C, we compare between it. So to melt all the ice, we need 6,000 calories. And the heat released by the water, it's only 4,800 calories. It means that the Q ice is bigger than Q water. Of the ice didn't melt yet. Okay. The reason why, because the heat needed to melt all the ice is bigger than heat released by the water. So the heat released by the water cannot melt all the ice. And now we need to calculate the mass of ice that melts. In the question C, we know that all of the ice didn't melt yet, right? So we only have the heat from the water, and we need to calculate the mass of ice that melts. So we use this equation. So the heat released by the water equal mass of ice times the specific heat latent from the fusion of ice. So the heat from water is around 4,800 equal of ice that melt times the specific latent heat of fusion of ice is 80. Okay, so the mass of ice equal 4,800 over 80, so it's equal 60 grams. Okay, next for E, we need to calculate the mass of ice remaining. In the question D, we already know the mass of ice that melt is around 60 grams. So the mass of ice remaining is equal the mass of ice in the beginning minus the mass of ice that melt. Okay, so it is 75 grams minus 60, so it's equal 50 grams. Now for F, we need to calculate the mass of water that should be added to make all ice melt. We can use these equations. The Q of water equal Q ice. Okay, because we just have 50 grams remaining of the ice, so we only calculating the mass of water needed that will make the 50 grams ice melt. So we need to calculate mass of water times C times delta T, and the Qm for ice just mass ice remaining times the specific latent heat. And then the mass of water we don't know yet, and the specific heat capacity of water is 1, and the difference temperature is 24 minus 0. Okay, and then the mass of ice remaining is 15 grams times the specific latent heat of fusion of ice is 80. Okay, so mass of water times 1 times 24 equal 1,200, and then the mass of water is equal 1,200 divided by 24, so it is 50 grams. Okay, so they need to add 50 grams to make all ice melt. Okay, this is the answer for question 1. Questions 2. The heat transfer through a composite wall is shown in the figure. Both the sections of the wall have equal thickness and cross-sectional area, but they have the different thermal conductivity. The left face of the wall is at 120 degrees Celsius and the right face is at 30 degrees Celsius. The interface temperature Ti of the composite wall is 60 degrees Celsius as shown in the figure 1. If the composite side was rearranged as shown in the figure 2, find the interface temperature Ti now. Is the interface temperature Ti shows the same value? Okay, so we need to find the interface temperature if the wall rearranged with a different arrangement. Okay, the first thing that we need to find is the ratio of thermal conductivity both the walls. This arrow is represent the heat flow. It is the heat flow from the higher temperature to the lower temperature. So in this figure 1, the heat flow from P to Q, right? But when we arrange the order of the walls, we make the Q in the left side and P in the right side. So the heat flow it starts from Q to P. So we need to find the interface temperature between them. Okay, to answer the question, first we need to remain the equation for heat rate flow for the conductions is equal K A delta T over L, with K is the thermal conductivity, A for cross-sectional area, delta T for the difference temperature, and L for the thickness. Okay, because we have wall P and Q, so we can make the equation become the heat rate flow for wall P equal the heat rate flow for wall Q. So Kp cross-sectional area for P and the difference temperature in wall P over thickness of P equal thermal conductivity for wall Q, cross-sectional area wall Q, and then difference temperature and the thickness of wall Q. Okay. In the question, we already know that both section of the wall have the equal thickness and cross-sectional area. So we can ignoring the A and the L. Yes, it is have the same. Okay, we don't know yet the thermal conductivity for wall P, and the difference temperature for wall P is 100 to 20 degrees Celsius minus 60 degrees Celsius. Okay, then the thermal conductivity of wall Q we don't know yet, and the difference temperature is 60 degrees Celsius minus 30 degrees Celsius. Okay, so Kp times 60 equal Kq times 30. So we can simplify this one. Divide by 30, it is getting 2 and it is getting 1. So 2 Kp equal Kq. What is the meaning of this ratio? It means that the conductivity of wall Q is twice than the thermal conductivity of wall Q. So Kq is twice than Kp. Okay, after we got the ratio of the thermal conductivity, we can calculate the interface temperature if we rearrange the composite side. So with the same equation before, we know we use HQ equal HP, but it is have the difference temperature, right? Because the wall Q now the temperature is 120 degrees Celsius, and the right side in the wall P the temperature is 30 degrees Celsius. Okay, so we can write KQ AQ and difference temperature per LQ equal KP AP difference temperature per LP. Okay, then we can eliminate the cross-sectional because both of the wall have the same or equal thickness and equal cross-sectional area. Okay, so we can write it KQ and then 120 minus Ti equal KP Ti minus 30. Okay, then in the previous calculation we already know that the KQ is equal twice of KP, so we just substitute the KQ. The thermal conductivity for wall Q is equal twice of thermal conductivity of wall P, so it is 120 minus Ti equal KP. The thermal conductivity for wall P is Ti minus 30. Okay, we can eliminate the KP because it is half same in both sides, so we can eliminate it and multiply it. So it's gonna be 2 times 120, 240, and 2 times Ti minus 2 Ti equal Ti minus 30. And then we can make it 240 plus 30 equal Ti plus 2 Ti. So it is 270 equal 3 Ti. So the Ti is equal 90 degrees Celsius. Okay, so we move back. Okay, in this interface temperature is 90 degrees Celsius. So if we rearrange the wall, it will be make the difference interface temperature. Okay, that is the answer for question 2.